All right. Let me just check the volume. We are fine. It's another beautiful day. Good evening, good morning, good afternoon, boys and girls. It's time for OSPF introduction. We're going to look at mastering OSPF fundamentals. Let's go. Let's go. So, the agenda for today we have link state routing protocols, OSPF characteristics, OSPF terminology, router ID related to OSPF, of course, the Hello protocol steps to create or form a neighbor relationship. OSPF, DR, and BDR, referring to the designated router and the backup designated router and OSPF packets. So let's start. First thing is first. So let's go ahead with the tables. We're talking about the tables right here. We're talking about the OSPF tables and the neighbor table, the routing table, and topology table. Those are the tables that we have. Now, what is the definition for each of those? The neighbor table is where router sends hello messages to discover their neighbors. Once it is determined that they can be neighbors, they are stored in that neighbor table. Okay, what else do we have here? What else? Topology table. It contains the entire network topology and all links. It knows all available routes, even if they are not used. And finally, the link state protocol uses the SPF shorted path first algorithm to select the best routes. So let's clear the drawings here. Let's move on. Let's learn more about it. What else do we have? Link state routing protocols continuity. So OSPF uses SPF, the Dijkstra algorithm. It creates or uses triggered updates and it sends periodic updates every 30 minutes. That's the way OSPF works. Okay, what else do we have? Now we have some of the features for OSPF. Give me just a moment here. And these will be, let me just activate the camera for a minute so I can just talk to you about them. So when we're talking about OSPF feature, we are referring to OSPF classless and allows summarization, fast convergence, a standard protocol. It preserves bandwidth, consumes a lot of memory and CPU, and it requires a hierarchical design. Next, these are some of the OSPF types that we're going to look up into detail. And we're talking about hello, DVD, that is database description. We have a link state request, LSR, link state update, LSU, and finally, LS act, which means link state acknowledgement. Those are the OSPF packet types. Let's move on. Let's continue learning about these more in detail. So now we have the definitions of each of those. So let's go. Let's go. Hello. What do we mean with hello? It uses, um, basically, it is used to discover neighbors and to establish and maintain adjacencies. OSPF header and neighbor mask, network mask, plus hello and that interval, options fields, router priority, DR and PTR addresses, and the list of discovered neighbors. In fact, we will learn more about that once we start doing the labs, of course. What is database description? It describes the content of that topology database. We have OSPF header plus packet sequence, number plus link state advertisement header. Link state request. It is sent by a router when it detects that portions of its database are out of date and during initial sync. It is used to request link state update, OSPF header plus fields, that uniquely identify the database information that the router is requesting. So far we went over hello, database description, and link state requests. What are we missing, guys? What are we missing? We're missing link state updates. So it carries one or more link state advertisements. It sends a response to a link state request. And finally, link state acknowledge or link state act. It responds to link state updates packets. It validates that the update packet has been received successfully, and we have an OSPF header and a link state advertisement header. That's basically a little bit of the explanation that we have for the OSPF packet types and a description for all of those. Let's continue learning. Now we're going to learn a little bit. Let me just clear the board. I don't like that drawing there. We're going to learn about OSPF terms, some of the terms. We're talking about area, internal router, APR, ASBR. What are those? What are they used for? So an area is basically where all routers share a common network topology. All areas must be connected to the backbone area 1. An internal router is a router that belongs to only one area. An ABR, area border router, is basically a router with at least one interface in area 0 and one or more interfaces in another area. And finally, Autonomous System Boundary Router, ASBR, a router that is typically connected to one or more logical entities, AS, through an external routing protocol such as BGP. Okay, let's go. What else do we have here? Okay, here we have the following. We have the way that we configure OSPF is router OSPF plus the router, the OSPF number. There's usually a number there. Then, in order to identify the routers, we have the router ID. So we configure, for example, if we are working with router 10, we configure the router ID of 10.10.10.10. It is basically like an IP address that we are configuring. And the way we do it, after running the router config in privilege mode, we do router OSPF and then the number. Let's say this is number 16. This is actually 56. Let's say it is 56 because we are going to look at a lab later on with that number. So this is 56. And then we do. What do we do? The next one is router ID, IP address, and let's do 2.2.2.2. And that will be for router 2, occur. So we can identify that specific router. The loopback interface with the highest IP address, it is basically the order for the router ID selection and of order priority. So router ID selection order of priority. In order to have that priority, we have the following path. First, we configure the router ID after adding the OSPF process number. Then we configure the loopback IP address, and the one with the higher priority is the one with the highest IP address. And finally, the physical or logical interface, the highest IP address of any active interface. Now, it is an IP address that identified the router in the OSPF process. What is this definition? With the explanation that we just have, this will be the router ID. So let's just write there, router ID. It is used in the DR and BDR election process for troubleshooting purposes. So let's go with the loopback. Remember the loopback with the highest IP address. There you go. Now we have a little bit of understanding on the router ID selection and order of priority. Let's clear the board. Let's continue moving forward. Next thing is the way that we configure it. So we do the config terminal. Then we start adding some information like the router OSPF and the process number. In this case is 100. And finally, the router ID is 1.1.1.1. And that's basically it. We are done. Let's just go ahead and clear the drawings and move forward. Next thing we do. Okay, some of the troubleshooting commands to look at OSPF are the following. Let me just use the highlighter for a moment. Let me use a better color for this. I have the green color. So show IP OSPF protocol. This is one of the famous ones. Show IP route OSPF, show IP interface brief, show IP OSPF interface, and show IP OSPF neighbors. So in order to troubleshoot, these are some of the most important commands that we will be using. And in fact, in some of the labs that we will build in the future, we will be using these commands. So let's clear the board for a moment. Let me just clear everything here. Let me just return to the red color for now. I need to change to a pencil with this. Basically, the line should be thinner. Let's just clear the board. Let's move on. Okay, this is also important when we're talking about hello and the timers by default for broadcast is 10 seconds and 40 seconds. For non-broadcast is 30 seconds and 120 seconds. For point-to-point is 10 seconds and 40 seconds. And for the network type point to multipoint is 30 seconds and 120 seconds. We're talking about hello and dead intervals default timers. Hello and dead timers, the default configurations are those we have just mentioned. Now, what are we doing when we are working with broadcast networks? We are accessing the following. We are accessing a multi-access that assumes broadcast capability. And we are going to participate in the DR and BDR election? Of course, we will. What about non-broadcast network type? Usually an example will be frame relay. Multi-access, but not broadcast. Manual neighbor configuration is required. And remember the timers, we have 30 and 120. And finally, yes, we will be having a DR and BDR election. What about point-to-point? For example, a serial link. Exactly two routers, no election is needed. That is 10 and 40 for the hello and dead timers. And there is no DR or BDR election. And finally, multi-point treats each connection as point-to-point. No DR or BDR, there's no election. And you can see it right here. And remember, the dead and hello timers are 30 and 20. Those are the default configurations for hello and dead timers. Let's go ahead and clear the drawings here and move on. What do we have next? Is actually the OSPF hello protocol. Okay, let me just use the highlighter for this one. We're going to use a green color. It's actually a yellow one, a yellow color. So for the router ID is a unique 32-bit identifier IP address. For the hello and dead intervals, frequency of hello packet transmission and timeout before declaring a neighbor is down. The neighbor list is the list of neighboring routers IDs. The network mask is the network mask used on the interface. The area is the OSPF area to which the interface belongs to. That's the one we're covering right now. What about priority? What do you think priority means and is used for? So priority is basically when the router have the highest priority, it is selected the designated router or DR. DR and BDR. IP addresses of the designated router is the DR, and the backup designated router, BDR. So those are referring to the DR and BDR. Usually one acts as a slave and the other one acts as a master. We will look that into detail later on during this chapter or this lesson. Authentication, there is a password authentication enabled usually, and the stop area flag, true. if the stop area is enabled. Those are basically some of the new terms that we are covering regarding OSPF Hello Protocol. So let's clear the board for a moment so we can continue moving on. The first thing you do, and basically this is to form a neighbor relationship using OSPF between two routers. At this moment, we are in down state. Down state. Look at that. And let me just change to a red color. And both routers are down. Basically, there is no communication. So nothing is happening yet. So let's see what start happening in order for a neighborship relationship between OSPF routers to finally occur. The router will send a hello, but there is no response yet because the neighbor is down. So the first thing it do, the router determines its own router ID. It adds the interface to the link state database as determined by the network command. By hello messages, it started working on it. Basically, it sends hello messages on that selected interface, and that's it. Next, something else happened. Let's clear the board, and we see init state. Init state. Let me just clear that line that we will not see because everything is in red. So what you can see right now is that we are sending a hello packet from router 1 to router 2. It is working as an init state. And the router sends this hello, but there is still not a confirmation and a validation that we have a match. So it receives the hello and it starts working on the hello on the timer's intervals, the network mask, the area, and the authentication key. Basically, it's validating that all of this information is accurate and properly configured and is matching in both sides of the connection. Next, let's continue moving forward. Let's clear the board for a moment, and now we are in two-wait state. This is when the second router that we're going to name now router 1 is going to be Nancy, and router 2 is going to be Donna. Finally, Donna or router 2 responds with the hello, and we finally start having that two-wait state. They are validating the parameters for authentication, the timers and hello timers are the same at both sides, and they are starting that communication. They are almost ready, but not fully, not fully. And you will see about that in a moment. So in step 5, it sends a hello back to the router. It checks, are we already neighbors? Yes, it resetted that interval. No, it add a new neighbor to the list. Let's go ahead and see what happened in step 6 of this. And now, remembering we're still having those router 2 and router 1 for Nancy and Donna, but we are moving to exchange state. And this is what happened. We're having the DVDs exchange, database description. They are being exchanged at this moment. And here is a summary of the LSDB. The other one and the other router replies, here is my summary of the LSDB. They are basically starting to share databases. The master-slave relationship in OSPF. They determine the priority, the router ID breaks the tie, the master sends a database description DVD packet, and the slave responds with its own uh, database description or the summary of the LSDB. That's basically when we are having the exchange process. Let's continue moving on. And finally, what do we have here? They are exchanging those DVDs. They are validating and confirming that those DVDs are all the information related to those. So the DVD says, I will start. The other one DVD says, no, you won't. They are basically negotiating information. this moment, when they are negotiating all those databases, all the information in the map of the different links that they have, the routes, we're having that XStar exchange, and we're almost ready. Not fully, but we're almost ready with the neighbor relationship. They are still negotiating. They are negotiating all those databases information, and this is the state. It is called XStar state. XStar state. Let's go ahead and clear the drawing and see what happens in the next step. And finally, we have loading state. We are almost ready, but what happened here? We are exchanging LSACT packages. After the acknowledgement and the link state exchange happened, we change at this moment from XStart state to loading state. And this is what happened. An ACT is sent for the received database, description, DVD, packet, and review. The slave requests specific network details using the LSR, link state request. The master may also request additional network details via LSR. Also, the LSUs are exchanged. So LSUs are exchanged, LSR are exchanged, and finally LSACT are exchanged. And we are almost ready. The master may also request the additional network details via LSR, and the slave then replies with its own LSUs. Once we finish all these negotiations for LSRs, LSUs, LSACT, we are going to jump into full state. And that's the next one that we are going to see. And we will be finally neighbors. OSPF was successfully completed. Let's take a look at this one and clear the drawings. Neighbors are synchronized. Yoo-hoo! We have done it. Amazing. We have full state. Tell me more about 2.2.2.0. No worries. Here you are. So they finish LSR, they finish LSUs, they finish the LS acknowledge, LSACT, and the full neighbor relationship with the two OSPF routers is finally completed. Great. So we did it. We have full connectivity. The OSPF neighbors are exchanging information and they know each other. That's the process. It's a little bit tedious, but finally we have connection. Great. Let's continue learning about OSPF. Give me just a moment. And the next topic I will explain in the next slide. But so far, let's try to understand a little bit. There is some code information from router 1 to router 2, from router 2 to router 4, and from router 3 to router 4. Usually there is a cost of 20 here, a cost of 10 in most of the connections between devices. Finally, there is a total cost of 30 to RTR2 and a cost of 40 to the route that connects to RTR3. So this one will have a total cost of 40, the first one over here on top, and this one I see the R2. This one apparently has a cost of 30, and this one has a cost of 40. So they are not counting everything yet. We're just counting this hop, and we got a total of 30 right here. We're counting this hop, and we got a total of 40 for the specific cost. We're still missing this jump and this other one. We will probably have a higher cost after that, but that's basically a little bit about the code. Let's go to the explanation that I have in the next slide to understand this better. Let's go. So this is the explanation. The OSPF path selection is based on cost. In that topology that we have just seen, RTR4 must be reached via this network, 10.0.0.0/24 network. It has two possible paths, the cost of 30 and the cost of 40. We saw those paths. The OSPF selects the lowest cost path, so traffic will flow through RTR2, which is actually a cost of 30. And this decision is reflected on RTR4's routing table, which prioritizes the route with the cost of 30. The diagram illustrates how OSPF uses cumulative interface costs to determine the optimal routing. That's the way that OSPF determines the best path. Let's continue learning about OSPF. And now we have the OSPF costs. There is a bandwidth of 100 there is a cost of 100 divided by the bandwidth. But we have the default ones. Here we have 56 kilobytes per second for a cost of 1785. 64 kbps, a cost of 1562. What is a T1 is 1.544 Mbps, is a cost of 64. The E1 has a cost of 48. The Ethernet has a cost of 10. Remembering the difference between E1 and T1, the T1 has 1.544 and the E1 has 2.048 Mbps. And finally, we have fast Ethernet, 100 Mbps with a cost of 1, and gigabit Ethernet, 1000 Mbps with a cost of 1 as well. So that's basically a little bit of understanding the way that the cost is measured in OSPF capabilities depending on the connection that we currently have. Let's clear the drawing and let's continue moving on with the next topic. And this is a summary of the OSPF types that we studied before. We studied a little bit about the kilos, the DVDs, the LSRs, the LSUs, and finally, when we were pretty much almost done, we have the LS Act, link state acknowledged. And after that, we have the full connectivity between OSPF. Okay, let's continue learning about this. And we have a summary of some of the topics that we have covered today. These are link state routing protocols, OSPF characteristics, OSPF terminology, router ID, hello protocols, steps to form neighbors, OSPF DR and PDR, and OSPF packets. Those are basically some of the topics and fundamentals that we have covered on this lesson. So I hope that you like this class, you learn a lot from it. It's been a pleasure working with you along today to finally understand some of the OSPF contexts and concepts as well. So until next lesson, I will see you at the top of success, boys and girls. It's been a pleasure learning about OSPF, and I will see you at the lab. We will be doing some Cisco packet tracer labs regarding this concept.